Do black holes have no hair? It is said that fact is sometimes stranger than fiction, and nowhere is that more true than in the case of black holes. Black holes are stranger than anything dreamed up by science fiction writers, but they are firmly matters of science fact. The scientific community was slow to realize that massive stars could collapse in on themselves under their own gravity and to consider how the objects left behind would behave. Albert Einstein even wrote a paper in 1939 claiming that stars could not collapse under gravity because matter could not be compressed beyond a certain point. Many scientists shared Einstein's gut feeling. The principal exception was the American scientist John Wheeler, who in many ways is the hero of the black hole story. In his work in the 1950s and 1960s, he emphasized that many stars would eventually collapse and pointed out the problems that possibility posed for theoretical physics. He also foresaw many of the properties of the objects which collapsed stars become, that is, black holes. During most of the life of a normal star, over many billions of years, it will support itself against its own gravity by thermal pressure caused by nuclear processes which convert hydrogen into helium. Eventually, however, the star will exhaust its nuclear fuel. The star will now contract. In some cases, it may be able to support itself as a white dwarf star. However, Subramanian Chandrasekhar showed in 1930 that the maximum mass of a white dwarf star is about 1.4 times that of the Sun. A similar maximum mass was calculated by Soviet physicist Lev Landau for a star made entirely of neutrons. What then would what then would be the fate of those countless stars with greater mass than a white dwarf or neutron star when they had exhausted their nuclear fuel? The problem was investigated by Robert Oppenheimer of later atom bomb fame in a couple of papers in 1939 with George Volkoff and Hartland Snyder. He showed that such a star could not be supported by outward pressure, and that if you take pressure out of the calculation, a uniform spherically systematic symmetric star would contract into a single point of infinite density. Such a point is called a singularity. All our theories of space are formulated on the assumption that space-time is smooth and nearly flat, so they break down at a singularity, where the curvature of space-time is infinite. In fact, the singularity marks the end of time itself. That is what Einstein found so objectionable. Then the Second World War intervened. Most scientists, including Robert Oppenheimer, switched their attention to nuclear physics, and the issue of gravitational collapse was largely forgotten. Interest in the subject revived with the discovery of distant objects called quasars. The first quasar, 3C273, was discovered in 1963. Many other quasars were soon discovered. They were bright despite being very distant. Nuclear processes could not account for their energy output because they release only a tiny amount of their rest mass as pure energy. The only alternative was gravitational energy released by gravitational collapse. Thus, gravitational collapses of stars were rediscovered. It was already clear that a uniform spherical star would contract to a point of infinite density, a singularity. The Einstein equations don't work at a singularity. This means that at this point of infinite density, one can't predict the future, which in turn implies that something strange could happen whenever a star collapsed. We wouldn't be affected by the breakdown of prediction if the singularities were naked, that is, if they were not shielded from the outside. When John Wheeler introduced the term black hole in 1967, it replaced the earlier name frozen star. Wheeler's coinage emphasized that the remnants of a collapsed star are of interest in their own right, independently of how they were formed. The new name caught on quickly. It suggested something dark and mysterious, but the French, being French, saw more risque meaning. For years, they resisted the name Trou Noir, claiming it was absence. But that was bit like trying to stand against Le Weekend and other Franglies. In the end, they had to give in. Who can resist a name that is such a winner? From the outside, you can't tell what is inside a black hole. You can throw television sets, diamond rings, or even your worst enemies into a black hole, and all the black hole will remember is the total mass, the state of rotation, and the electric charge. John Wheeler is known for expressing this principle as a black hole has no hair. To the, to the French, this just confirmed their suspicions. A black hole has a boundary called the event horizon. This is where gravity is just strong enough to drag light back and prevent it escaping. Because nothing can travel faster than light, everything else will get dragged back also. Falling through falling through the event horizon is a bit like going over Niagara Falls in a canoe. If you were above the falls, you can get away if you paddle fast enough. But once you are over the edge, you are lost. There's no way back. As you get nearer the falls, the current gets faster. This means it pulls harder on the front of the canoe than the back. There's a danger that the canoe will be pulled apart. It is the same with black holes. If you fall towards a black hole feet first, gravity will pull harder on your feet than your head because they are nearer the black hole. The result is you will be stretched out long ways and squashed in sideways. If the black hole has a mass of a few times our sun's, you will be torn apart and made into spaghetti before you reach the horizon. However, if you fall towards a much larger black hole with a mass of a million times the sun's, you will reach the horizon without difficulty. So, if you want to explore the inside of a black hole, make sure you choose a big one. There is a black hole with a mass of about 4 million times that of the sun at the center of our Milky Way galaxy. Although you wouldn't notice anything particular as you fell into a black hole, someone watching you from a distant distance would never see you across the cross the event horizon. Instead, you would appear to slow down and hover just outside. Your image would get dimmer and dimmer and redder until you were effectively lost from sight. As far as the outside world is concerned, you would be lost forever. A dramatic advance in our understanding of these mysterious phenomena came with a mathematical discovery in 1970. This was that the surface area of the event horizon, the boundary zone around a black hole, has the property that it always increases when additional matter or radiation falls into the black hole. This property suggests that there is a resemblance between the area of the event horizon of a black hole and conventional Newtonian physics, specifically the concept of entropy in thermodynamics. Entropy can be regarded as a measure of the disorder of a system, or e- equivalently as a lack of knowledge of its precise state. The famous second law of thermodynamics says that entropy always increases with time. In the, the 1970 discovery was the first hint of this crucial connection. Although the existence of a connection between entropy and the area of the event horizon was clear, it was not obvious to us how the area could be identified as the entropy of a black hole itself. What would be meant by the entropy of a black hole? The crucial suggestion was made in 1972 by Jacob Bekenstein, a graduate student at Princeton University, who later worked at the Hebrew University of Jerusalem. It goes like this: when a black hole is created by gravitational collapse, it rapidly settles down to a stationary state, which is categorized by only three parameters: the mass, the angular momentum, state of rotation, and the electric charge. Apart from these three properties, the black hole preserves no other details of the object that has collapsed. This theorem has implications for information. In the cosmologist's sense of information, the idea that every particle and every force in the universe has an implicit answer to a yes no question. Bekenstein's theorem implies that a large amount of information is lost in a gravitational collapse. For example, the final black hole state is independent of whether the body that collapsed was composed of matter or antimatter, or whether it was spherical or highly irregular in shape. In other words, a black hole of a given mass, angular momentum, and electric charge could have been formed by the collapse of any one of the large number of different configurations of matter, including any one of a large number of different types of star. Indeed, if quantum effects are left aside, the number of potential configurations would be infinite, since the black hole could have been formed by the collapse of a cloud of an indefinitely large number of particles of indefinitely low mass. But could the number of configurations really be infinite? This is where quantum effects come in. The uncertainty principle of quantum mechanics implies that only particles with a wavelength smaller than that of black hole itself could form a black hole. That means the range of potential wavelengths would be limited. It could not be infinite. It therefore appears that the number of configurations that could form a black hole of a given mass, angular momentum, and electric charge, although very large, may also be finite. Jacob Bekenstein suggested that from this finite number, one could derive the entropy of a black hole. This would be a measure of the amount of information that was irretrievably lost during the collapse when a black hole was created. The apparently fatal flaw in Bekenstein's suggestion was that if a black hole has a finite entropy that is proportional to the area of its event horizon, it also ought, it also ought to have a finite temperature, which would be proportional to its surface gravity. This would imply that a black hole could be in equilibrium with respect to thermal radiation at some temperature other than zero. Yet, according to classical concepts, no such equilibrium is possible, since the black hole would absorb any thermal radiation that fell on it. But by definition, would not be able to emit anything in return. It cannot emit anything, it cannot emit heat. This is a paradox, and it's one of which I am going to return in my next lecture, when I'll be exploring how black holes challenge the most basic principle about the predictability of the universe and the certainty of history, and asking what would happen if you ever got sucked into one.